So what does it mean for a machine to be athletic? We will demonstrate the concept of machine athleticism and our research to achieve it with the help of these flying machines called quadricopters, or quads for short. Quads have been around for a long time. The reason that they're so popular these days is because they're mechanically simple. By controlling the speeds of these four propellers, these machines can roll, pitch, yaw, and accelerate along their common orientation. On board are also a battery, a computer, various sensors, and wireless radios. Quads are extremely agile, but this agility comes at a cost. They are inherently unstable, and they need some form of automatic feedback control in order to be able to fly. So, how did it just do that? Cameras on the ceiling and a laptop serve as an indoor global positioning system. It's used to locate objects in the space that have these reflective markers on them. This data is then sent to another laptop that is running estimation and control algorithms, which in turn sends commands to the quad, which is also running estimation and control algorithms. The bulk of our research is algorithms. It's the magic that brings these machines to life. So how does one design the algorithms that create a machine athlete? We use something broadly called model-based design. We first capture the physics with a mathematical model of how the machines behave. We then use a branch of mathematics called control theory to analyze these models and also to synthesize algorithms for controlling them. For example, that's how we can make the quad hover. We first capture the dynamics with a set of differential equations. We then manipulate these equations with the help of control theory to create algorithms that stabilize the quad. Let me demonstrate the strength of this approach. Suppose that we want this quad to not only hover, but to also balance this pole. With a little bit of practice, it's pretty straightforward for a human being to do this, although we do have the advantage of having 2 feet on the ground and the use of our very versatile hands. It becomes a little bit more difficult when I only have 1 foot on the ground and when I don't use my hands. Notice how this pole has a reflective marker on top, which means that it can be located in the space. You can notice that this quad is making fine adjustments to keep the pole balanced. How do we design the algorithms to do this? We added the mathematical model of the pole to that of the quad. Once we have a model of the combined quad-pole system, we can use control theory to create algorithms for controlling it. Here you see that it's stable, and even if I give it little nudges, it goes back to the nice balanced position. We can also augment the model to include where we want the quad to be in space. Using this pointer, made out of reflective markers, I can point to where I want the quad to be in space, a fixed distance away from me. The key to these acrobatic maneuvers is algorithms, designed with the help of mathematical models and control theory. Let's tell the quad to come back here and let the pole drop, and I will next demonstrate the importance of understanding physical models and the workings of the physical world. Notice how the quad lost altitude when I put this glass of water on it. Unlike the balancing pole, I did not include the mathematical model of the glass in the system. In fact, the system doesn't even know that the glass of water is there. Like before, I can use the pointer to tell the quad where I want to be in space. Okay, you should be asking yourself, why doesn't the water fall out of the glass? 2 facts. The first is that gravity acts on all objects in the same way. The second is that the propellers are all pointing in the same direction of the glass, pointing up. You put these two things together, the net result is that all side forces on the glass are small and are mainly dominated by aerodynamic effects, which at these speeds are negligible. That's why you don't need to model the glass. It naturally doesn't spill, no matter what the quad does. The lesson here is that some high-performance tasks are easier than others, and that understanding the physics of the problem tells you which ones are easy and which ones are hard. In this instance, carrying a glass of water is easy, balancing a pole is hard. We've all heard stories of athletes performing feats while physically injured. Can a machine also perform with extreme physical damage?